students, welcome to our channel Chemistry Physics, where physics gets charged. The last video I discussed vector form of Coulomb's law. So now in this we'll discuss the force due to multiple charges, right? So previously we are discussing the force between the two charges only when the two charges of Q1 and Q2 separating by certain separation. Then the force is 1 by 4 by epsilon Q1 Q2 by R square. But now if we are taking the set of charges, like here one point charge is placed at point O, and the several charges of Q1, Q2, Q3, Q4 and so on are placed at different distance of R1, R2, R3. Then what is the net force on this charge due to rest of the charges is we are going to discuss now, right? So further, according to vector form of Coulomb's law, as we discussed in the last video, so here let these are both are positive charges. So this charge Q will experience the force because of first, and it is a repelling force. So line along the line joining two charges only the force will be present. So it is a F1 bar, and due to second charge along that line only, here it is the F2 bar, and like that here is the F4 bar, and this is F3 bar, and so many charges are there at last F1 bar. These are the directions of forces acting on charge Q due to rest of the charges. So that according to principle of superposition, the net force on this charge can be written as the vector sum of F1 plus F2 plus F3 and so on. F1, it is not the addition of all the forces, it is a vector addition, please. When I am stating the vector addition, you should consider the angle between the two here and the direction simply, right? And the one more important point is here, while you are considering the force on Q due to this Q1, on this F1 force, there is no effect of the remaining charges of Q2, Q3, Q4. And while you are writing the force for a charge Q on Q2, so that there is no effect we are consider rest of the charges like Q1, Q3, Q4. Means simply whenever we are taking the force between the two charges, it does not affected by the presence of any other charges nearer to it. That is the meaning of that point. And according to that here, F1 bar is equals to 1 by 4 pi epsilon Q, Q1 by R1 square, like Q, Q2 by R2 square, depends on the number of forces. And here Q and 4 by epsilon is common, so that we can write Q1 by R1 square plus Q2 by R2 square and so on. So this is not the addition of forces, it is the vector addition of forces. To understand this, I am coming to one example here. Let I am taking the equilateral triangle, each of side R, and here the three charges of identical and the same charges and same magnitude of plus Q are placed at three corners. I need to find the net force. I'm going to find the net force on any one of the charges. On any one of the charge here. Means for a convenience, and I'm supposing this is the first charge, it is the second charge, this is the third charge. And according to this, I am supposed to find the resultant force on the first one. It is vector form, magnitude as well as direction I am going to find here. Okay, so here as I am finding the net force on this, here in this system there is arrangement of three charges at three coordinates of a equilateral triangle, right? So now this first charge is experiencing the force because of second as well as because of third. Once again, the charge first is experiencing the force because of 2 as well as because of 3, and 1 and 2 are the like charges, so the nature of force on first due to second is a repulsive. When it is a repulsive, the direction should be along this, and this is named as on 1 due to 2. Any problem with this? And now at the same time, on the first charge there is a repulsive force due to third charge. Why? Because again first and third are same sign of charges, so that along the line joining them, this is the F1 3 bar. Means here this first particle is experiencing the force because of 2, and as the three charges having the same magnitude and having the same separation, so that can I state the force on first due to second should be equal in magnitude with the force on first due to third, and that is equals to, we can write 1 by 4 pi epsilon Q square by R square, Q1 Q2, Q into Q is a Q square upon the separation is a R, so R square, and in the respective direction. and the angle between them is a theta. Theta is angle between F12 bar and F13 bar. Is there any problem with this? And this theta, as this is the equilateral triangle, this angle is definitely of 60 degrees. So when it is 60 degrees, it is also be of 60 degrees. Means can I write theta is equals to 60 degrees. Now I am coming to the point from parallelogram law of vector. When the two vectors of same magnitude and the angle between them is theta, the resultant of the two vectors is 2f cos theta by 2. F resultant on first is equals to 2f12 cos theta by 2. Otherwise, we have from parallelogram law vector under root of f12 square plus f13 square plus 2f12 f13 cos theta. I will write here. Actually, the resultant of first is, according to parallelogram law vector, f12 square plus f13 square plus 2f12 f13 cos theta. By substituting and simplifying, you will get the answer. But to solve the same problem within two steps, it's a very important point from parallelogram law of vector in the special cases. You may go through my video there in the previous time I added, right? So there, when the two vectors of same magnitude and angle between them is theta, then the resultant of the two vector is simply 2f cos theta by 2. Based on that, here I am coming to f12 is what is given here, and the cos theta by 2 is the cos 60 is nothing but 60 by 2 is the cos 30. So the 2 into 1 by 4 pi epsilon. So q square by r square. Cos 30 is a root 3 by 2. So that we can write root 3 times of 1 by 4 pi epsilon q square by r square is the resultant force on first due to second and third. And to know the direction here, as the resultant is definitely in between the two only. So this is what the direction of resultant on first. And again from parallelogram law of vector, in the two vectors of same magnitude, and an angle between them is theta, then the direction alpha is given by half of the angle between them. Means here alpha is equals to, we have theta by 2, which means alpha is equals to what you can write? 30 degrees. This is the way we can find the direction and magnitude of the resultant by using parallelogram law of vector by simple shortcut here. Of course, by this you will get, and again to this finding alpha, we have tan alpha is what? Q sin theta by p plus q cos theta. Means f13 cos theta by f12 plus f13 cos theta is a very lengthier one. But when you have that trick, means that the special case which we have discussed, so that you will get within a one step the resultant. And one more important thing, I am asking here as the first particle. If they are asking in the second or third particles are same only. If they are asking in the second, due to the force on second due to first is repulsive, is along this. Force on second due to third is also repulsive, is a 2, 3, and this is the resultant here. But again we are getting the same magnitude only. Why? Because the charges are same, separation is same, the magnitude is same, but the direction is different. Please see, the resultant force on this is along this, so that the resultant force on this is along this. Similarly, you may write on third due to first, due to second, and this is the resultant. This is the way we can solve the problems due to multiple charges by using vector addition. If you have the commanding on special cases of vector addition, so that you can solve within two steps, otherwise you need to go through the multiple steps here. Okay, and again for yourself, I am giving two problems here. You need to find, let I am taking this is a positive charge, here is a negative charge, and this is a positive charge. Okay, this is a 1, 2, 3. Okay, you find the resultant force on first and the resultant force on second. This is for you. If you are getting my point, then trying to solve this. If you are getting the answers, you may check from your materials so that you will get this concept here. Thank you, students. Thank you for watching.